Hello, I'm Nick Kramer for the seventh time today. Uh, Today I'll be presenting enhanced UAS availability via vehicle-to-vehicle routing scaled experiments. This is research done at NASA Ames Research Center with my interns Chris and Gordon and collaborators Rick, Elena, and Sean Grabby and Eleanor Raffel. So to start with, I'm going to start with talking about a motivation, go into problem formulation, then move into the vehicle setup, experimental setup and results section, followed by the conclusion towards the tail end. So to start with our motivation, as many of you are probably aware and probably experienced or might have enjoyed yourself, UAVs have become a common sight with hobbyists. They're incredibly popular. They're a fun hobby and activity. But beyond that, they're actually a serious commercial venture now. So to sort of help this realization of how do we incorporate all these things that are enjoyable but also can be a service to our general population, NASA focused on the integration of them into the national airspace and proposed this Unmanned Aerial Systems Traffic Management, or UTM. So if you look at the left over here, you can sort of see that the concept of this. So you've got routes going in and out the city. So you've got these blue, these yellow, the red, and the light blue sort of going through the city. And these potentially could be delivering packages or doing some crop dusting or performing very critical emergency services as it's showing with it over the fire. But all of these things, the one of the most crucial pieces is operation beyond line of sight. So in order to effectively manage beyond visual line of sight operations, the vehicles must always be in contact with the operator to ensure compliance. To the left here, you can sort of see this diagram of various means of the vehicles and how they're going to be communicating to each other or to other services through that. So the reason for this is typically when we're sort of operating one of these remote vehicles, we are still in this direct C2 environment, right? Where we are essentially acting as the pilot, just not sitting on board, right? So that means we are responsible for everything that the vehicle is doing, and we're ready and there to either land it safely or kill it if there's no other choice. But once you go beyond visual line of sight, you no longer have that capability. So what you need is you need constant feedback from the vehicle to say, I am where I am supposed to be, I am doing what I'm supposed to be, and the configurations I'm supposed to be doing them. This allows you to then be able to report back to the UTM system and show that you're being compliant, right? And that's how we really need to do this to manage our safe operations. Now, one of the things though is what that means is if you have a vehicle that's out of contact for more than 30 seconds, the vehicle must land because at that point the vehicle cannot be justifying or communicating back that it is in a safe condition, right? Uh, but that's not a really great solution. That's not what you would like to happen. And the reason is landing's risky. And it's especially risky when you don't know exactly what's going to be around. Maybe you've identified a safe landing spot, but then you still have to sort of perform the highest risk scenario without any sort of oversight there. So really what you want to do is you want to increase the vehicle's availability. And when you do that, that increases the safety, but that also expands the UAV operations. So that's really what we're looking at. We're trying to increase the vehicle's availability. All right, so what does that problem look like? So there's been a lot of research in the past that sort of looks into vehicular ad hoc networks. And so one of the major problems that this sort of always has had is it always sort of is exploratory, right? So if you look at it with the idea of cars, right, coming through the intersection, car A does not know that car B is going to be there approaching. So they have to discover each other. And so that discovery process, is really sort of has quite a bit of overhead. So you have to do that before you can decide to communicate. You have to establish where things are going. You have to be able to tell expectations of disconnect and reconnect, or if the vehicle just stopped responding. There's a lot of complexity to that. But the beauty of sort of this UTM system is you can always, so the vehicles will always sort of have a federated system of telling it where they're going to be. So it's either going to be checking out a voxel, or it's going to be reporting a flight path, or it's going to be doing something like that. So then from there, we can sort of make this graph, as we have demonstrated on the right side here, at each individual time set for what we think they could be communicating, and we can update that sort of weighted graph in response to known issues, right? So if you're going around a corner of a building, you lost line of sight, you don't expect that you'll have communication from those vehicle to vehicles anymore. But what this really sets up is this sets up a graph problem that every time instance on this sort of rolling iteration at a very large scale, you want to solve a spanning tree problem. And you don't want to solve it just once, you want to solve it multiple times, because you can sort of see, and you want to have multiple best tree solutions. It's because you can sort of see on this right hand side, even though you might have the expected black graph, your actual green graph has a lot less connectivity, right? So reality gets in the way. And so you want to have multiple sort of good routes so that you can still get back to your ground station. Now, in this case, your ground station doesn't necessarily have to actually be an operator sitting behind a ground station. It can be anything that is connected, right? You can go back to a Wi-Fi hotspot. You can go back to another vehicle that has LTE capabilities, or anything like that. You just need to get to something that will get you back to the ground station. And then by doing this, you can use the other vehicles to do that. So this sort of formulation is, it scales, it gets pretty large, and it is well suited for solutions that quantum computers actually can solve. So that's actually where this research was trending, and we have other papers that are forthcoming on this. But to sort of build up this capabilities, we have to prove that this is actually a realistic assumption, that we can do this vehicle to vehicle with UAVs today. So to do that, we sort of look at and think about what sort of vehicle is realistic, right? And so one of the things we started with is we said, okay, we want to just use as much COTS hardware as possible, right? This is the sort of stuff that any hobbyist can get, so anyone can do and build the system up. So from there, we also said, okay, well, let's make this a little more challenging. Let's really put some realism in it and say, well, a lot of the times you'll have lost this line of sight communication, or you're lost in communication in general. You're actually not going to have GPS as well. So we actually went and started using Visual SLAM as our localization capabilities. We used Intel NUC to run ORP-SLAM on ORP-SLAM 2 on, but that NUC was our redundant network, vehicle-to-vehicle network, where we created the ad hoc network. And then the PixHawk had a direct line communication, exactly like you would expect in a real environment. Okay, so we're really focused on realism, but we want to sort of constrain the problem to something that we can solve effectively with vehicles that will be there, but maybe not so much flying around in a high-risk environment like actually in a city block. So what we did is we said, okay, well, let's take a couple city blocks and we're going to scale this down and put it in a building. So we created these PVC pipe structures in the NASA Small Unmanned Aerial Systems Autonomy Research Complex, Newark, and we sort of set it up, and this gave us a good motivation to say, you sit there and you take a laser and you point and you say, okay, well, I would have lost line of sight through these sets of points, and this gives us a good motivation to sort of create that loss of line of sight map and where the communications might not be. So that's great, but PVC buildings don't actually create communication failures for us to work with. So we had to think about how we wanted to do that. The building's small, you have good connectivity. So really what it came down to is we said, all right, well, the application layer is where the money's at. We can just update our ad hoc network with the appropriate sort of expected routing table that we could have that then could act as a vehicle limit. So that's cool. So we sort of need to integrate that into our whole big software design plan. So this is what we're looking at here. We sort of start from this left-hand side here with this initial flight plan generation. So this says, hey, I'm going to drop off package X at location B. So I'm going to take flight plan, Q. Whatever it may be. From there, you say, okay, well, now I know my flight plan. I have sort of a general idea of where my beyond line of sight and my communications would drop out. So I'm going to create, and I also know where everyone else's flight plan is. So I'm going to create routing tables. I'm going to push that to my ground station. It'll take those things, combine them all together, schedule the waypoints, keep some backup of the results, and then deploy them to the vehicles, and the vehicles will update their ad hoc network associately, and it will also do some updates and object detection and avoidance, and so that'll need to go back and be replanned in that case. So we didn't actually implement all of this. We started with sort of the lowest level, make sure, yes, we can do this. But from there, we had to have this application layer disturbance that I was sort of describing before. That's basically looking at the location it currently is and updating in response to that to disturb our network. Great, so that's all fantastic, but as it turns out, your primary point-to-point radio isn't something that you want to disturb. So it's actually not meant to be able to be turned off during flight. Makes a lot of sense. You don't want to accidentally turn it off during flight. That would be bad. So this really forced us into this 5-layer disruption for this this connection. So what we ended up doing is we just dropped the power all the way to the middle. That wasn't enough. So what we said is, okay, we're going to put an antenna that's really not meant for this. It's not the right frequency, and it's probably a not something we would do for long term because it's like a recipe for burning out your antenna. But for a couple flights, it'll be good enough. We use some RF damping foam to reduce the ground station side, and then even put up some reflective aluminum foil on the corner we wanted to block. And so all those things combined gave us enough that we were able to consistently lose connection going around a particular corner. That's all great. So like I said, you can sort of get to these really complex scenarios, but we wanted to start with something that was just nice and simple, right? So we have a leader and follower. They're going around the block, really a couple blocks. And we, for example, in this case, we know that we have a window washing robot that's going to be washing windows on that little cross-shaped building down there. So that's going to be our routing, our relay node. And we'll sort of fly around the leader and follow in response to that. So we did that, and this is what it actually looked like. Great, our router vehicle hung out there and cleaned the windows. The leader and follower followed their path. You can sort of see that the follower didn't follow it quite as well as the leader did. This was sort of a case where, some of it's just variation of the vehicles. We were using a lot of hobbyist commercial off-the-shelf stuff. They vary quite a bit with that, especially some of the electronics, the ESCs. But you can see that sort of yellow areas where we were able to rig it up and get our telemetry connection lost. Okay, so this is all fantastic, but did we actually kill that connection? So what we're looking at here is on the top plot up here, we can really see that we're looking at the round trip delay time. So essentially what's happening is over that primary telemetry, that 915 megahertz connection, you're occasionally pinging to sort of assess the health of it. And so you can see that more or less everything's in the same place. And then you get a dropout of communication. And then a reconnection of communication, right? So it's around the same corner as for each vehicle. So we were able to sort of say, okay, yes, look, it had no communication, and then when it reconnects, it had this really, really long ping time, right? Which is why that top one's a logarithmic graph to sort of just keep it on there. So this tells us that yes, we effectively blocked that communication avenue to flight. But if you remember, what we were really looking for was the goal of this wasn't for us to try to block communication. It was try to increase availability through ad hoc network, right? So that vehicle to vehicle. So what you're seeing here is the ground station position frequency update, which is to say Even though in the previous slide we had, 30 to 40 seconds of blackout period as we went around there. In this case, you're seeing that you never dip below 10 hertz, right? And so essentially, we pretty much always see a dip in the frequency update while it's transitioning between primary communication capabilities, right? So it dipped, but it dipped to 10 hertz, which is nowhere close to that 30 hertz or 30 seconds that you would need to sort of have the dropout. And for our scaled model, 30 seconds was probably closer to 4-ish seconds, but even, we're updating at 10 hertz. So we're still well above that. So this shows us that, yes, that backup vehicle-to-vehicle network, and when the primary communication network went down, worked and allowed us to sort of route through that relay node and maintain availability of the vehicle. So this was all great. What this really showed is that with the current technology, using this vehicle-to-vehicle communication, you are able to maintain connections. Sort of this mental idea of setting up these spanning tree problems and solving them quickly and having it as a backup plan to enhance availability is something that you should be able to do, and you should be able to do it with modern hardware. And could be very helpful to sort of integrate into something that might be a supplementary service provider for the UTM scenarios in the future. But a lot of what we learned was that while testing seems like a great idea, inside seems like a great idea at time, controlling the realism really set up sort of these experimental problems. It was a lot of work to get the experiment to sort of tailor to what we wanted. We were using visual slams. We weren't using some unrealistic localization capabilities that would allow us to really tune in the problem. So the vehicles were still needed to be able to carry the onboard processing power and payload, right? So essentially they needed to have that NUC, right? You might be able to replace the NUC with something else, but it still would need to be something that's powerful enough and beefy enough to do some visual processing, which is probably what these UAVs are going to need in the future anyways. So there was only so small we could scale the vehicle down. But to scale the city down to fit in there, now the vehicle proportions, the vehicle scaled like a 1:3 sort of ratio, whereas the city scaled a 1:24 ratio. And the accuracy of the visualization system is still pretty good, half a meter sort of waypoint good. But when you scaled your city down and you have a quarter of a meter for your streets, you're literally in a tight spot now. So a lot of those sort of scalings of the system down to that, to keep that realism, to sort of keep it relevant and speak to what the capabilities are today, really put a lot of stress on us, and were one of the biggest problems. But we did it. We were able to show that this should work, and really it ended up being a higher bar than we intended. So if you went and you did the exact same thing outside, now you have GPS the vast majority of your time. And so you're not depending on that. You have a lot, even if you're flying down a city street, you have a lot more space than we had. And you can still sort of do those communication connections, and it can maintain those, and you can sort of, and updating the routing tables and sort of that piece in a a priori fashion without having to explore and establish best routes, just sort of spam the prescribed ones, are all pretty good and should be a functional way to operate. So I want to thank you all for listening to me in sort of this unusual condition, and I hope the video wasn't too painful.